Okay, so this is a quick video designed to take you from zero to hero when it comes to thermal expansion and stress. Okay, so what does all this mean? Let's say you got a piece of metal, in this case it's like a long thin rod, and you add a little bit of heat to it, right? Well, what happens when you add heat to something? Its temperature increases. But in addition to its temperature increasing, it grows. Whenever you heat anything, it grows. And the question is, how much does it grow? Well, it depends on the kind of material you're dealing with. So the amount it grows depends on its original length, how much you increase the temperature by, and then this alpha, this is called the coefficient of linear expansion, and it just basically tells you about the kind of material it is. So just a couple of things worth noting, like, why does the growth depend on the original length? That's puzzling. Certainly, it should depend on the kind of material. That's plausible. And also, why does the thing grow at all? Well, remember that all materials are actually made out of a bunch of atoms, and the simplest model we can have for this system is a bunch of atoms connected by springs. And if you think, well, that's ridiculous, atoms don't have springs connecting them, it turns out that for any system, so long as you're near equilibrium, which means so long as it's not changing by a lot, then you can always approximate the system as springs, as a spring force. That's a subject for another video, though. For now, just take my word for it. You can approximate for small expansions that it looks like a spring. Well, what have we been saying about temperature the whole time? The greater the temperature, the faster things move. If this guy's a little block on a spring and I make him move faster, he is going to swing back and forth with a greater amount of amplitude. And that is true for every single one of these atoms. I pump energy in, they start moving faster. If they start moving faster, the springs stretch a little bit. And that also explains why the amount it grows depends on the length. The more length I have, the more atoms I have. If each atom experiences a little tiny bit of growth delta L, well, the more atoms I have, the little delta L's will add up to give me one big delta L for the entire material. Okay, so that's where this formula comes from. Okay, now what happens if I decide to push on the ends of this thing? Okay, so one way to make something grow is to pump energy into it, but the other thing I can do is I can smush things by pushing on them really hard. And if you remember, the way that things smush when you push on them hard depends on something called the Young modulus of the material. In other words, if I push on something with a certain force and it has a certain cross-sectional area, this guy, by the way, is called stress. It's really a pressure. I don't know why they call it a stress sometimes and a pressure other times. Maybe somebody else knows the answer to that, but they always call it stress in this case. The stress in this case depends on the length and the Young modulus, the kind of material it is. And again, you see that the length depends on the change in length again. And you might wonder, well, okay, with temperature, I get it. The things are bouncing around. You have more things bouncing around. It's going to grow more. Why does it depend on the length in this case? Well, in this case, the load, if you put a load on one of these guys, he transfers the load to all of his buddies through these springs. And the more of these buddies you have, the more the load gets distributed. So that's the idea behind that. Okay. Now the question is, how hard do I have to push on this? How hard do I have to push on this in order to push it back to its original length? In other words, it had grown. Now I want to push it back to the original length like it's shown. How hard do I have to push on it? Well, we can say that the change in length due to my pushing has to be equal to the change in length due to my thermal expansion. One is pushing inward, the other is pushing outward. And if that is the case, well, then I can do a little bit of algebra and I can solve and say, okay, great. This is how hard I should push on the ends of it in order to make it not grow when I put heat into it. You can see that the bigger I make the temperature, the more the thermal stress becomes. So you can't do this forever. Eventually, the thermal stress you cause or have to push on this thing so hard that you're going to exceed the strength of the material and you'll break it. Okay, so this is called the thermal stress of the material. Okay, so now a question arises, what happens if instead of having one rod, you have two rods? Seems like an entirely different setup, and you might guess something like, okay, all right, I put heat into it, I push on both ends, there's two objects now, so maybe the stress is like the sum of the two stresses. Except the thing is that forces don't work that way. This force is pushing on this side, this force is pushing on this side, and that force gets translated through all those little springs inside all the way to the end, so that the force on these atoms over here is the same size as this force over here. And the stress from this guy is the same size as the stress over here. That means that these two metals have to push on each other exactly as hard as these two things are pushing on each other. Now, since they're pushing on each other by Newton's third law, the stresses have to be opposite. In other words, what we're saying is the stress on A has to equal the stress on B. They are pushing on each other, and by default, the universe, by conservation of momentum, guarantees that the stress on both metals is identical. Okay, so what does that mean? That means that if you wanted to find out the total change in length, you'd find the change in length on A due to thermal expansion, plus the thermal change, plus the change in length of A due to stress, plus the change in B due to thermal, plus the change in B due to stress. In other words, take all the delta L's, pretend all of these are separate things. This guy's got forces on him, and he's also being heated. This guy's got forces on him, and he's also being heated. I get that they're pushing on each other, but that'll all somehow magically work itself out in the stress terms. We just need to add these all together, and if we do that, you end up with something that is equal to 0. Why should it be equal to 0? It's equal to 0 because I'm holding it in place. I'm preventing it from growing. In other words, the total change in length, delta L, is 0. So let's actually write out the terms for that. The terms look something like alpha 1 times alpha L1 delta T. So this is the thermal term, stress term, thermal term, stress term. I just take them individually and I add them up and I set them equal to 0, and then boom, a little bit of algebra, and I get something for the thermal stress, which looks a little uglier than before, but it's really not so bad, right? So you say, okay, well, good, that's enough. But actually, it's not enough. I want to know what happens if now I add a third rod. You can see where this is going. We want to be able to eventually handle the case of as many rods as we like, right? And so you might say, oh, this is so hard. Now we've got 3 things. We've got 2 different interfaces. We have to figure out all the stresses on everything, but actually, you don't, because everything we said before is still true. This force gets translated through this material until this point. This force gets translated through this material into this point. So this guy has to push on this guy as hard as they push on each other, and so on and so forth. And it's like a Newton's third law party. All the stresses are the same. Whatever stress you put on any of the materials, that's going to be the stress on all the materials. And so we can do the same trick we did before, only now I have 3 terms. So now I have LA, LB, LC, and if I do all the algebra and I add it all up, I end up with something that looks like this. And here I didn't write all 3 terms. I just wrote the general case, because now instead of having 3 or 4, you could put as many of those next to each other as you like. So is this an important formula? No, not particularly. I mean, maybe to somebody it is. That's not really why I wanted to show you this. What I wanted to show you this is, if I had started with this problem and I said, find the thermal stress on this 3 material problem, you'd go crazy. You'd say this is too hard. There's too many different dynamics going on. But the strategy, it's the strategy I want to point out. We get a complicated effect by considering the sum of little, small effects. And we say that the total effect is the superposition of all those little effects. And it turns out that this works. This technique works for most systems in the universe. You're allowed to use this principle of linear superposition. And you've seen us use this same technique of adding a bunch of things in, say problems involving calorimetry, where you add up the heat, right? So this technique is something that you'll use over and over and over again. And it's really the technique you should focus on rather than this particular formula. Okay, hopefully this was more helpful than confusing.